Bismillahirrahmanirrahim. The development of numerous models for MOSFET stems from the inherent complexity of these devices. The variety of the operational condition the MOSFET encountered. MOSFET operate in different region, cutoff region, triode region, and saturation region, each with distinct electrical behavior that must be accurately captured for effective circuit design. As these devices exhibit complex behavior under varying voltage and current, multiple models are essential to predict the performance of the MOSFET accurately and ensure reliable operation in an array of electronic systems. Now we discuss the feature of model which are common for all regions. And here the parameter B, also known as a transconductance parameter in MOSFET, is defined as beta is equal to Kp multiplied by W over L, where Kp represents the process transconductance parameters and W is the width of the MOSFET channel and L is the length of the channel. This relationship highlights how the MOSFET ability to control current flow is influenced by its physical dimension and technology used for its fabrication. A larger value of W over L ratio increases beta, which enhances the device transconductance, which is crucial for many electronic applications required high gains and efficiency. Understanding these relationships is essential for optimizing MOSFET performance in various electronic circuits. Similarly, the process transconductance parameters Kp for n-channel device, which can be defined as Kp is equal to mu n COX, where mu n is the electron mobility and COX is the oxide capacitance per unit area. This equation illustrates the dependence of the MOSFET performance on both the mobility and charge carriers, electron in this case, and the capacitance of the gate oxide layer. However, higher electron mobility leads to the better conduction characteristic, while a large oxide capacitance enhances the gate control over the channel, allowing for improved switching speed and overall device efficiency. Understanding AP is very crucial for designing the and optimizing the N-channel MOSFET in various electronics applications, particularly in high speed and high performance electronic circuit. On the other hand, the condition Ig is equal to 0 and Ib is equal to 0, gate current 0 or body current 0 signifies that the gate and bulk current are effectively 0, which is the key characteristic of the device. This high input impedance allows the MOSFET to control output parameter with minimal input current, making it efficient for switching and amplification application. Now we discuss NMOS model for cutoff region. In the cutoff region, when VGS gate to source voltage is less than the threshold voltage, the drain current IDS is equal to 0, and this indicates that device is effectively switched off, preventing current flow from drain to source the terminals. As a result, the MOSFET behaves just like as an open switch, ensuring minimal power consumption and allowing for the precise control in digital circuits. In the triode region of the MOSFET, where VGS minus VT, which is also called override voltage, is greater than or equal VDS. Drain current, then IDS, is described by the equation IDS is equal to beta VGS minus VT minus VDS over 2 multiplied by VDS. For VGS minus VT should be greater than VDS and VDS should be greater than 0. This relationship highlights how the current increase linearly with the drain current voltage, the VDS, as the channel is formed and enhanced by the gate voltage exceeding the threshold. In this region, the MOSFET operates effectively as a variable resistor, where the current flow is influenced by both VGS and VDS. This characteristic is crucial for many applications like analog switching and amplifiers, allowing precise control over the output current in response to the input signal. Now we discuss about the saturation region of the MOSFET. In saturation region of the MOSFET, when this expression we discuss that IDS is equal to B over 2 VGS minus VT square 1 plus lambda VDS, where we see that lambda is basically 1 over um, early voltage, and it is also 1 plus lambda ds account for the channel length modulation, which slightly increase the current as VDS rises. Operating in this region, yani saturation region, allowing the MOSFET to function efficiently as a current source, making it ideal for amplification and switching application where stable current output current is required despite variation in the voltage. Now we discuss about the threshold voltage because all these region depends on the threshold voltage. Threshold voltage is equal to Vt is equal to V2O plus gamma under root VSB plus 2 sigma phi f minus under root 2 phi f, where is a bulk voltage and phi s represent the Fermi potential. This relationship illustrates how the threshold voltage varies with change in source bulk voltage due to the body effect, which occurs when the body potential influences the depletion region. As VSB increases, the threshold voltage also rises, affecting the device turn-on characteristic. Understanding this dependency is very crucial for designing circuit that require precise control over MOSFET switching behavior, particularly, especially in application where body biasing play a significant role in performance and efficiency. Thank you.